Okay, so for today about operation, if you still remember, we talked about the process stage. I mean, last time we have five different stage, and then we add the interrupt or like 2 interrupts, and then we also have the setting for the interrupt. We setting the queue, right? Okay, so I give you with these. This time I still working on the one like the key setting up and also the Linux system. So I'm not yet complete. So how many of you able to run the C purpose, or like can you execute the Python on your computer? For the Mac, I think you don't have any issue to execute the G purpose. And how about the Windows? Like, can you execute, or like last time I think you used the EC2 to set up the Ubuntu. Can you execute or like install the C purpose?
I got the interrupt UI that you.
Yeah, I provide. Yeah. So okay, you can execute the PY. PY is the Python. So Python, I just like give you 2 options in case. Okay. So you see right here. It's pretty simple right here. So just like we running a loop and then just executing. So I need to ask you like if we need to modify or change anything like how can we do that? But are you familiar with the Python? Oh, no, okay. But I know if you are working on the C purpose, and then we can discuss because okay, we need to set up. Then I really need to hurry up to set up the environment. So let you auto connect. Okay. For the lab, actually, I want to let you know how can we simulate like the first one, the fundamental, just like changing from the new stage and then put it to ready, and then put it to running, waiting, and then terminate. The suppose is the complete cycle. So from the sample code I gave you, why not look at the C purpose? So right here I have the process. And the process, we will define the name and then start with new. And then from the new, we will execute, okay, I have a process called P1, pass it into it. When I pass it, and then I will execute the run. One will be transist to ready. So the transist to ready, I will pass the stage and then just print it out. Okay. And then next, I will pass it to running. Okay. Then based on this one, if you can execute the Python or somehow, then how can I get 2 processes? Because this one will be combined. If you want to, you can refer to the last week right here. If we have the lab last week for the process, like we try to fork to create the parent or like we have the multiple because the last time because we stuck at the one I said setting up the environment. So before we start to work on that I would like to like follow up with the last week because we spend much of our time on it. So right here, then we can start with the last week lab. Okay. So if you still remember the last week, just like simulate, actually when I execute, so I tell, okay, if I have 2 the process that I using a fork to create the first one. So the fork will be create a child process. So 2 processes will be exactly the same. So they have their own PID, process ID. Okay. So they're exactly same. So that's why we need to consider if we have the same process, but we call the child, they're not really same, but we are identical source code. So they will execute. That means we have a possibility to get the same resources, right? Make sense? Okay. So that's why we need to check the status. And that's why when we in the last previous, no, the 2 weeks ago, we talked about the case like when we have two processes need to get resources, then how can we doing the loop? Yeah, like using while loop wait to check the flag, or like when I have multiple resources. That's why we need to do that, to check and free after we use the resources and free. Okay. For question 2 is like, okay, let's say I asking right here say, okay, I have a free resources and then with two processes, then how can I grade it? So I give the example code. So if you remember. Okay. And right here. And then because like based on the one, if you still remember, then I will let you to do some exercise and to experience. Okay, so how can I change to a queue or like waiting? If you remember, we have the last time our lecture we cover will be the stack queue. Right here we have the queue. So we have the ready queue processor. Then how can we modify? Okay, from here. Here's the basic. So what if we using a C purpose or Python? Just maybe Python we don't have exactly the queue, or then we need to array to pretend. Okay, so just using the loop for loop to access it. Then that's what we are going. Here's just the result. I can execute. All right. If you look at the source code, I just like call it like with the specific number. Then we have the interrupt. Because we are all the source code is just like pretending how it works. Maybe later when you get one more assignment to with the editing, then you need to modify the code. They say, okay, how can you simulate or like adding the queue to handle the process? So I will give you some time to do that. And we go back to the note right here. Okay. And for the interrupt process, if we still remember, right here, the interrupt. So when we are executing, when we in the source code right here, we were using, okay, if I detect it's a number, then I will print out as the interrupt and handle, and then say to interrupt handler, and then sleep for a while. So that's how it actually works. So if I get the interrupt, I will this process to sleep and wait, or like for waiting for certain time, or like I will put it back, wait, and then I say if we have a interrupt queue, so I will save to the queue. Because it's going to happen is that we have multiple interrupt happen when we executing, and then you are like when we have multiple process, we are using the round robin or like list time, then we need to like taking turns. That's how we work. For this later for the assignment, then we need to modify the source code to do it. And after we finish, we will join it and then execute again. This part is the Python C purpose will be right here. Let me show you. Check it again, interrupt. Okay, so right here you will see the same if I follow and waiting. So every time, because like if we don't wait for simulation, because it will print out really quick, print out everything. So we just like put a time sleep. And let's say for the I equals to 2, I have I trigger this interrupt happen. So I will send it to the function. So you will see like we always have function to handle the interrupt. So we save and handle it. So we just like simulating, okay, if I have an interrupt comes in for the original process, I wait for it and wait. When like, so we using time sleep for 2. So after we wait for it, just pretending, okay, we are handling another process. And then once it complete, then we say, okay, it's complete, and then we'll come back and then one thing the loop. And then after we finish the loop, then the process complete. So it's pretty easy and simple, straightforward. Later, how can we handle with the loop, the queue? Then we will cover later. Okay. That's how we're going to use. And mainly, we need to know the interrupt handler. Handler is a function. We need is a for handle the interrupt. And for the process function, we just simulate a process that like trigger the interrupt in the midway. So we need to do. And third thing, so the third is used to simulate the process execute and handle the interrupt. So you will see right here. But we didn't have it right here, but you can see the third thing right here, main, and then third thing. So we have different process function. Maybe it's too small. Okay. So actually in this source code, we compile like 3 parts. One's the third, and then the interrupt handler.
Oh shit, I forgot to grab health potions. Please, let me go back.
Okay. Yep. So in the main process, right here, the process function, you will see, okay, we're just like simulating from the first one. And build the range of 5 web process, and then just like pretend we are working, and then just slow down, then sleep, and then we just like put some of the trigger. So we just simulate, because we are not really like have a OS. The triggers get a new input or interval comes in, so we just preset. Okay, and for the logic, we just are using a third thing. The third way we have a target is like process function, so it's right here. So we say, and then every time we start the thread, and then we jump, and then the one. So just like follow the syntax, but for the OS, we are not really like cover all the function like talking about Python. If you're interested, then you can study a little bit of it. And also the syntax for here's the Python, and another one is the C purpose right here. So if you check the C purpose, it looks slightly not the same, but we have the thread right here to call the handler. Logic is the same, but we have the different syntax. Okay. And okay, so if example, you will think, okay, so what the different stage observed in the first script? So what's the first script? Yes.
What is the STD from the CI?
Okay, if you know the C purpose, so we sometimes use the called the standard input, that one. So STD. Most of the time we're using the namespace STD to replace it, so we don't have to put it. So do you remember?
Been a while since I've seen that.
Okay. For the getting the in out, the IO, so that one's like printing. So we have the called the STD, the standard input, and it's part of the syntax, like, but it looks stupid. Then you can remove it. Let me go. No, but we can using the like for the using namespace. If you remember using namespace, if you remember this one, yeah, STD, and we can like remove the right here. Where is it? Yes, STD right here. So you can use the CL directly. Do you remember? Okay, but because we are not like teaching the CPAPs right here, so you can review up later. And okay, so we are mainly like just like try to demonstrate, or like when we're talking OS, so we know okay, so when we have a new process, we always start from new. So when we move on, we need to load, then we always put it to ready, and from ready we move to the running stage. But we have sometimes we have some time limit, so we are not cannot really like complete the whole process. Then we will put it back. to ready and wait, or sometimes we have some interrupt comes in, then we'll go to interrupt queue. Like if we have like one interrupt state, then just put it to interrupt and wait for it and put it back to ready queue and execute again. So all this will be like simulate the state. Okay, so terminate, that means when you finish. So that's how it looks like. And then the follow-up, okay, how does the interrupt handler function affect the execution of the process in the second script? So right here, so the interrupt handler function simulate the handling like as an interrupt. So when the process reaches the point like when the interrupt trigger, but we already preset it. Okay, but in reality, like in the OS system, so we always have an interrupt comes out. So interrupt say we know for like or waiting for certain input. Okay, so sometimes they maybe you may be confused with you say, okay, interrupt is like something I don't know. Actually, it's like I'm waiting for something to interrupt. Like for the code, if there's something interrupt we didn't expect, we throw the error. That kind of interrupt, then the OS cannot handle it. Then we always like maybe crash or but it's really hard. If something's out of the expectation, we get the deadlock or like we don't have a safe mode. Okay. But for those that we know, then we can have an interrupt to handle it. So we will know how to do it. And we always like try to lock it just like pretending, okay. We just right here, we put in 2 seconds sleep and then goes back and keep going. So when the process like effectively pause until the interrupt handle is complete, then we will continue the execution. That's like how the process life it works. And then the process stage and interrupt handle simulate the real world scenario in operation system. Okay, so you will see all the stage right here will be like from new, ready, run, waiting, terminate. So it's excellent. So all this stage can help manage the process scheduling and resource allocation efficiency. We don't talk about the scheduling yet. So scheduling will include the like different mechanism, like how can let the process like taking terms like with different time. But we are not discussing in this part, so we just need to okay. And after like let's say we are in waiting stage and we are not using the CPU resources, and how can we put it back to ready state and then like run again? And the interrupt handling say, okay, when the interrupt comes out, sometimes like asynchronously. So asynchronously is like we have the original like state, 5 states, but the interrupt always like suddenly comes in. So in interrupt. So we need to get that like immediately attention. So we need to handle it. So maybe you say the hardware, keyboard input, maybe we have some like network package or server, like we have a system call, we can do it. So all those comes in, then we need to take action in. So we will suspend the current process, so save it and then execute the interrupt. So if we still remember the diagram from the, let me see, in the process, and it's not here. I think it's before the previous chapter, if you remember. So when we have an interrupt, we will jump to another like memory, stop our main memory, execute, like take it, execute and go back to the original one. Okay, that's how it works. So that one is a simulation. If you're interested, you can try to modify, like try to change the queue, but also the assignment, I will let you to do that. Okay, so let's go back to our where we stop. Okay. So last time when we talked about the PCB, the process control block. So we are all like including all the structures right here, like scheduling, data structuring, then in the process communication, process privilege, memory management, and also the resources like ownership and utilization. Okay. So right here, the process control block, like the most important data, we say contain all the information, so all the details, but you don't have to really like memorize all, like, but you need to have a rough picture. No, and then you should know the those blocks like are read or like can be modified virtually, like every modules in the OS, and they define the stage of the OS. But the problem is like, or difficulty, we are not talking about access, but the protection. Because a bug in a single routine can be damage the PCB. It can also destroy the system ability to manage and affect the process. And the design change in the structure, like symmetric of the process control block, could affect the number of the modules in the OS. So because like all the control block, if we go back to here, the control block will be about all the scheduling, status information, or the data structure. Is it possible destroy or like modify or the memory have like changing bit? Because everything saved on the main memory, just like 0 and 1, right? So if you know sometimes we do the checksum, to checking the status. So because sometimes we have to checksum, even checksum can help, but it doesn't mean also it can prevent the change of the data, because when we change one single bit, maybe checksum can figure out, but when they change like 2 different bits, then the checksum still the same, but we have an error. So that's why what it says the protection. Okay. If you know, then we will move on right here, the control and execution of the process. So we need to know understand some of the requirement and issue need to be successful support the process by OS. So for the execution, we have one or more is called the less privilege mode, or the user program typical execute in this mode. Or the system mode will be more like privilege, and also referred to like control mode or like kernel mode. So kernel, we heard the like kernel of or if you still remember the diagram, we have the application, and also we have the hardware, right? And you will see there's a layer, the diagram called kernel. Then what's kernel? Do you still remember what's kernel? Also, it mainly handle with kind of like you just imagine it's a bridge, because we don't for the application, we are not really directly controlling the hardware. Okay, let's say I send a printing job to the printer. Are we really like, when we sending a printing job, are we really need to like translating the whole Word document or PDF document to like bits, and then the bits that sent to the printer, and then how the printer aligning the location? We don't have to do that, because the kernel help us to handle it. So what we need to do just mainly focus on the application layer and say to the kernel. So kernel would help us to translate, and then just like interact with the hardware part. Okay, that's what the kernel doing. Okay. So it's like kind of like really the bottom or like foundation of the whole system. Okay. And you will see like typical function. We talk about the typical function of the OS kernel. So let's say for the process management, including the process creation, termination, scheduling, dispatching, process switching, synchronization, also like support the inter-process communication, manage the process control block. So this like one part of the OS of the function kernel is like the process management. And the second thing is about the memory management. So we need to like allocate the address to the process. So it will help us to manage, okay, when we create a process, there's a program, and then there's a process, then where we will put on the main memory. So that's the OS kernel we do. And then wrapping, because when we loading from the memory to CPU, CPU load it, or like when we have a VM, when we don't have a sufficient main memory space, we say we have a virtual memory. So we will create for EC2, I remember other command we can define when we create the server, the memory size, we always can set the size of the swapping. So maybe like 256 megabyte. So the normally that's for that one, the size it won't be like really large. Yeah, it's just helping. Also, we have the page and segment management. So for this part, we also going to cover like when we need to loading the data from main memory to the CPU, like when we handle, we will have called a paging. And the IO, the buffer manager. So because from the input of our like the IO devices, actually is really slow. So when the buffer is the helper to read all the input and then set it. So it will increase the speed and also allocation of the IO channel and devices to the process. And the support function right here will be the interrupt handling, accounting, and monitoring. So that's what it's doing. For the process switching, processor switch may occur anytime when the OS scan the control from the current running process. So if you remember the state like in the running, and possible events give the OS controller like interrupt. So because when the interrupt comes in, so reaction to a synchronized event, external trapping. So like handling an error of exception condition. If you remember, if some source code we have like try, catch, like those. So we will know, okay, how can we handle? Sometimes we do have some error without trying. So they will throw it and then pop a message. So that's how the process, it will like switch out and then go to that. And supervisor call. So we will try to call an operation system function. This one we will talk about it. Okay. When we talk about interrupt, so due to some like soft event, it's a external to and independent of a current running process, like the clock interrupt. Clock is represent, we have the timer for the process. So when we have like maybe timeout or sometimes something happen, then we have interrupts from the clock. And the IO interrupt is most common, we know the keyboard or some input camera. And then we have the memory fault. Also the time slice, the maximum amount of time that the process can execute before they being interrupted, like this. So it's going. The trap is an error execution condition generally within the currently running process. So the OS determines like if the condition is a fatal and moved to the exit stage and then process like switch occurs. So if the stage like near ready running, we have the exit. So just put the exit. So we're not executing. So the action will depends on the nature of the error. There are some errors that are uncatchable, or like some we can catch it, then we can just put it to exit. That means that when the OS can catch it, but if no, then we always like could cause the if we cannot get the resources, then we would like, it's common, like let's say the system down or like it freeze. That's like common way happen. And when we change of the process state, so the step in the full will be switched like this. Okay, we will save the context of a processor and then update the PCB. So if you still remember inside the PCB, we have the state of the process. Okay, so the information, and then we move the PCB to the queue. So the ready block or like ready suspend. So if you still remember the graph, we'll put over there and then select another process of execution. So we will assign another one to there and then update the PCB process select, and then for the example state is now running. So will be next one, and then update the memory and management structure, current process state, VM state. So all this like keep follow up, because When we change the process, then that means the memory location we need to update. So they're followed by, and then we need to restore the context of that process to CPU register. That's the how process like we need to switch. So if you know if the currently running process is to be moved to another state, then the OS will make a substantial change in its environment. So this one means even we need to like change to another process, or we always the OS need to make sure the resources is enough for next process. If not enough, then we are not executing that one. We still go to. Okay. And when we're doing this, we need to know like the security issue. So right here we discuss the implication of the process and security in the OS. So for security issue, so an OS associated with a set of like privilege of each process. Typically, a process that execute on behalf of the user has the privilege that OS recognized for the user. Also, just like setting the like permission, like allowing it. And highest level of privilege is referred to the administrator, supervisor, or root access. So if you still remember the right, like using the account, root account, especially in a Linux system. So when we create the server or like install it, we always come with the root. So root is the default name. We have the highest right. So if we do it in like cybersecurity, if you remember, if you list it, you see some file is under root, right? Okay, so they are like have a highest. And then when we create the user, the first user account, so will be the administrator. So administrator, it doesn't mean it's a root, but you can try to get the like kind of like second highest. If for sometime we get the what is that called using sudo good, if you remember, so we can change the using sudo to modify the content, even though they're under like root permission. And the key security issue in the design of any OS is to prevent or like to list detection attempt by a user or the malware program from getting unauthorized privilege on the system and getting root access. So this one, I think you're pretty easy to know. So for that, to this, so the object is to gain the access to the system or like to increase the range of the privilege accessible on the system, and then they try to attempt to accrue the information that should have been protected. And for others will be like have a threat. They are all, they can be like relatively harmless or something really damaging. And if you know the Windows system, like when we talk about the OS Windows system, we have lots of like backdoor like executing. Sometimes they open the port, or like we have most of the time those service or application when they execute, they will allow to change the permission, or like they have the right to access certain folder or directory. So if you remember, I think if some of you in the morning class we talk about that IAM, you're asking, okay, we can read it, but we can execute, right? But most of the time when we execute a batch file, BAT, the batch file. So for those commands, we can like change the permission, and sometimes some scripts, like when you install a program, they will execute, like they will maybe attach a script. So they will change the code. Most of the time it's pretty common, they will change your file permission, or they try to delete certain files, or they will encrypt your file. Okay, that's what they did. So that's why we say try to give the always a less privilege to say, okay, it's read only or execute. And but that one is not pretty common. What you say? Have you ever experienced pretty common? I think the injection is about the web browser. Have you ever try to click on something, the link, and then like the browser pops out. It did happen to me is this one time. Okay, I reinstall my Mac and then need to install the Adobe. And then when I open the browser, it pops out. Okay, you need to update your Adobe. So I just click on the button. So unluckily, that one actually is a skip. So it's not a really Adobe update. So it powered the website, but because I sometimes the timing, the perfect timing, I reinstall my Mac and then I just like install Adobe. So it comes out. And actually, that one is like it override the original privilege, and then it will install. There's a like script in behind, so running install. Most of the time, if you experience will be, they will attach the called the homepage URL. So when you when you open your browser, they always redirect to a certain homepage. So they rewrite your original one, or they will remove the rights of certain application. That's what they do. So for the counter measurement, like so for the detection, so you see that security service that monitor and analyze the system events for the proposing funding, provide real-time and near real-time warning of attempt to access the system resources in an unauthorized manner. And then maybe host or network based. And I can share yesterday, because we invite there's a guest speaker. He shared about he worked in the Tesla before, and then so he talked about the cybersecurity and also share about his experience, like how they the team, because they realized there's some website pretending they're like company, but they like not really sharing which company. So they will send an email and say, okay, you need to input your information, and then they will have a payment. So they try to set up like how to investigate, checking, okay, where the IP registered, and also they will checking, okay, when they have a payment, where did they send to? So also that the data center with the ISP, like what those like involved. So they will chase all these things. I will see if they are going to share, and then it's okay. Then I will share that video, like the meeting to you, so you'll see how they really operate, like really in company level for the security. Okay. So for the instruction detection system, IDS compares the three logical components: sensor, analyzer, and user interface. And then the IDS are typically designed to detect human into the behavior, as well as the software behavior. Still boring stuff. Okay, keep going. So the process of verifying an identity coming by or for a system entirety is right here. And authentication process consists of two steps: identification and then verification. And then for journal means for user identity is something user knows, user owns, user is, and then the user does. Okay. Still the information. And then when we implement a security policy that's specific who or what may have access to each specific system resources, and the type of access is they permit in each instance, mediate between a user, system resources, security administrator, maintainer, authorization, database, and auditing function, monitor and keep the records of user access system resources. Okay, access control, everything. So right now we will talk about the Unix process management. So right now, how can we implement? Still some history. So about the Unix like SVR4, so the use of the model of most like OS executing within the environment of the user's process. So system process run in the kernel mode. So when we see the kernel mode, so it's directly deal with the hardware and execute the operating system code to perform the administrative and housekeeping function. That's what we're doing. And then the user process operates in the user mode to execute user program, and utility operates in the kernel mode to execute the instruction that belongs to the kernel. And enter kernel mode by issuing a system call. And when an exception is generated or when the interrupt occur. So for the system call is the sometimes for the interrupt comes out, so we will call the system. I have a system call, and this system call will call another function to handle it. So most of the time it's the OS read or the implement. How we're going to handle this this interrupt. So it's like kind of preset system call. So when we call it, or if you see the script statement, you say just have a call, system call, and that's it. Then they will call it from the library. It will handle it. So right here, the Unix process stage will be right here. So user running user mode, kernel running, and then ready to run in memory, ready to run as soon as the kernel schedule it, asleep in the memory. So when we are unable to execute until the event occurs, so the process is the main memory, just like we call a block stage. And ready to run, put the process ready to run, but the swapper must swap the process into main memory before the kernel can schedule it to execute. Okay, sleeping and swap. So the process waiting an event and has been swapped to a secondary storage. So if you know the block stage, we're transferring you will see the secondary storage will be the hard drive. So actually in the whole process, when we handling program, we always moving from the if you see the status is changing ready, running, and then maybe we have a block or suspend. So actually in physically, what we are doing, we are actually moving it from the main memory, maybe to the CPU go back. So when we are running, we are from main memory, put it to CPU execute, but put it back. And when we are stop it terminal, then we need to block, then we will put it back to the hard drive. Okay, because we need to free up the memory space. But when we are ready, then we will load it from the hard drive back to the main memory. And then we have the preemptive. So process running from the kernel to the user mode. And then, but the kernel preempted it, and those processes switch to schedule another process. So here all the status they're doing, and then create. So process newly creates and not yet ready to run. And we have the zombie. So zombie is that the process no longer exists, but it leaves its record for its parent process to collect. If you know the garbage collection, sometimes for the advanced level language, we need to do it free up the space, even C purpose too. So if we try to create something, remember to remove it or free it after we use it. And here's the whole picture of the Unix process state transition. So we can start with let's say we can start with the ready to run. When we try to create, if we have a simulation, have a fork, have a parent-child ID, so we always create a new process. So they will check do we have enough memory to do that? So yes, then I'm ready to run in the memory. If no, then I just okay, swap out. So swapping, remember, from the memory to the hard drive. Also, sometimes we will try to create a VM, the virtual memory, to save it. But physically, because the VM also we using part of the hard drive, so it's way slower than the main memory. Okay. So in the whole behind the kernel, what they're doing, they really just swapping in out, just moving it from the ready to run, or they're changing. So if they are kind of waiting right here, so they will right here say they'll put as a sleep or waiting mode. So when they wake up, depends on maybe a time, or maybe they're not yet ready. we are waiting for another input. So we will put it into the sleep mode, sleep, and then we are waiting. Okay, if we are ready, we get our input, then we'll wake up and then put it back to main memory to execute it. Okay, Treble is right here. And then if we are ready, like from the main memory, okay, we are schedule the process to really execute the kernel running. So the kernel is like really execute like in the bottom layer, right? If you still remember. If right here is we have interrupt, and then after the interrupt complete, then we'll go back to kernel running. And when we have right here, if you still remember, we talk about user running. So when the kernel finish running, it will send it to the user running. Sometimes we have the system call. So when the system call occur, or we call it the interrupt, so we go back to the kernel. The kernel will execute. So we'll put it like the user running, we wait for it. We need to handle with the interrupt first, and then we'll go back. And also preemptive right here. So we will send it to the from kernel to it, and then it's ready. So you will see the right here preemptive. So the process will running from the kernel to the user mode, and the kernel preempt it, and then just the process switch to the schedule, another process. So we just free out and then get a new using process and send it back to the kernel running. And when we exit, it become a zombie. So just waiting for it. And then because this one, we only looking for one process, but we do have a child and parent. So the parent level, we do have it. So we need collect. And we have the process, we have the user level context. So the process text, so it's an executable machine instruction. So it's the assembly code, so for it. And then the process data, the data accessible by the program of this process. And then use the stack, contain argument, local variable, pointers of other functions in the user mode. So here will be mainly is the program that we create all the variables instructions. So will be stored right here. Share the memory. So memory will be shared with other process. So use to the inter-process communication. That's I physically be doing. And we have the register contents. The register will be including the address of next instruction, and will be executed maybe like in the kernel or user memory space of this process. And then the process state register. So we contain the hardware status at the time, like preemption, the contents, and then the format are like hardware depends. So this one is like more like on the hardware. And the stack pointer, it points to the top of the kernel or user stack. So it depends on the mode of the operation at the time of preemption. And then general purpose, the hardware dependence. So all this will be the user context. So lots of things, just like remember the instruction. Okay. And the system level context. Okay, so for the system context will be the process table entry. So it defines the stage of the process. So this information is always accessible to the OS. And also the user area, the process control information that needs to be accessed only in the context of the process. When we say what's the user area, and then the preprocess region table, so defines the mapping from the virtual to physical address. Also like contains a permission field that indicate the type of access or process, like read only, read write, or like read execute. The kernel stack, so connects the stack frame of the kernel, the procedures as the process execute in the kernel mode. You will see lots of terms right here. You will get the pictures, and then later, let's see, I can create something can simulate, so we can have a better picture, like all these things are working together. Lots of times, just know the names, but we are not really like really to use all this information to learn it, and then keep going more like information. So the process stage is about the current state of the process pointer. So like to the user area. So when we say the pointers, like the process memory area. And then the process size enable the operation system know how many space to allocate the process. Then the user identifiers, so the real user ID identifiers, so the user use in response for the running process. And effective user ID may be used by a process to gain the temporary privilege to associate with the particular program. If you still remember, like we have the creator user. So for the user, we have the user ID. So it just like talk about, okay, the real user ID we're using. Okay, while the program is being executing as a part of process, the process operates with the effective user ID. So we need to know, like when we execute the program monitoring. Let me see. Okay, it comes out. Okay. So right here you will see we talk about the user, right? So you see some like under my like this user account, this is how I install it. And then some of them that belongs to the root. So I say it's the root account, and then maybe we have other like Windows Server. And you can see others MDM response nearby. So you will see they have a different type of user. Some of the user we are not like really see, because when we build the system OS or the kernel itself, we require like some specific user, or like we have different application, and those application will create some user. So they will also have their own user ID. So we will more than what we imagine if the cybersecurity, we try to do some user account, those we are like controllable by us, like we create. But also for the application we install, they will require to, actually when we install, so there are certain script to create their own user. Also, they will get a user group. They will set up the permission to access their files, their program to do that. And then the PID, the process ID, will be for it. So the ID of the parent process, and also they say when the process enter the create state during the fork system call. So you will hear the system call. So one of it is the fork. Okay. And the event descriptor. So whether when a process is in a sleeping status. Okay. So when the event occurs, the process is transferred to a ready to run state. So this is how we're doing. And then priority used for the process scheduling. Later you'll know the priority. So it's the number indicate. But we can modify the priority later, like maybe in different time. So we can change it. And we can, based on the mechanism for the scheduling, then they will like process earlier or like have higher priority, then we'll put it like before another process. Signal like enumerate the signal sent to the process but not yet handled. This is called the signal. Timers include the process execution time, kernel resources utilization, and the user set timer used to send the alarm signal to a process. So here's the timer when we talk about it. And then the p-link, the pointer thing, the pointer to the next link in the ready queue. So we have the queue. So here's we calling for the 5-stage process. When really in the implementation, we have a queue to save all the process. So here's when we say the p-link is about it. And then we have the memory status. So it indicates that whether the process image is in the main memory or is already swapped out. So if it's in the main memory, then definitely will be indicate whether it's maybe swapped out or they temporarily locked into a main memory. So it's just a state. Okay. So we know all the keywords, all the terms. Then we talk about the like process creation. So the process creation means that the kernel system call. So we fork. So that we if you remember the lab, the first one, the basic one. So this we do. So because like in the kernel mode, we do it. So after creation, the process like the kernel can do one of the following. So either like stay in the parent process, transfer the control to the child process, or transfer the control to another process. So actually we can like in the fork system call. So when you remember the the last time we only show the first one. Okay, we have two. So actually we have multiple system call. So like fork and then we have multiple child. So maybe we will like transfer from to the parent to child, and then the child also have another system call. So we have a stack, like then I'll go to like another child, and then we will print it. Okay. So that's how it looks like. It's like most of the fundamental concept right here is like here's a modern OS system in the process. And then the principal function of OS is try to create, manage, and terminate the process. That's what you need to know. That's the OS. And also in the process, we need to know we have a PCB. So you heard a lot about the PCB, and then it's like all the information required for the OS to manage the system. Like the application, so include the current state, resource allocate to a priority. So when we study or like in this OS, so here's like the key information you need to know, like what's the current state, so what the resources need to allocate to it, and then what's the priority, because all these will affect the scheduling. That's what we cover later. And the stage will be like start from new will be ready, running. Okay, we have the block with like terminate all these states, and running process is like the one that currently being executed by the processor. So when we're talking execute, but if you remember the Unix system, so we divide into user mode and kernel mode. So kernel mode is like user execute in the application, and then we need to send it to the kernel way. Kernel is like communicate, kind of like bridging, help you to convert the like software application to really physical with communicate with the hardware. Okay, so it's two steps right here. And a block process is waiting for the completion of some event. So when we talk about it, and sometimes when we block, maybe we will put it like from the main memory, put it back to the hard drive, like in the waiting. So for running process, it's the interrupt either by interrupt or by executing a supervisor call to the OS. So here's the like lots of definition, just need to know. And when we really go into the like some of the process, then you will know more details about it. So right now, most of it is like kind of just like definition, like talking about what's the process, all these things. So something boring. Some of them maybe when you need it, just recall back to the table, say what's the process and memorize it. So some of them we are not really use it, but some of them, yes, we are always saying about it. So we will, when we talk about something really about scheduling, preparing, like the VM swapping, so offset, then we'll know. Just like mainly you need to know most of the information we store in the inside the PCB. If you still remember, there's a picture, there's a called a process image. Where's the process image? Right here, we have the process image. Where's the image? So over there, image. Okay, the process image. So right here. So where we store. So just have a rough picture, like in this moment, still lots of like theory, and then just like something you just need to kind of like remember, and that's it. And that's it for today's class. Thank you. Yeah, throwing things.